Hello, everyone. Let's start. So, welcome to reorg.wtf Summit. This is our series of in-depth technical discussion on blockchain security related topics, brought to you by Flashbot's MEV Fellowship. You can visit the latest agenda and check out every speaker's slides at reorg.wtf. Yes, that's the link. And you can check back for the latest recordings after every speaker speak on Crowdcast on your top left-hand corner. And there will be all the sessions that are being recorded. Without further ado, let's get started with Georgios presenting on the types of blockchain reorgs on various consensus algorithms. Georgios, please feel free to start.
Yep. Thank you, Tina. So, as Tina said, we'll be talking about reorgs across consensus algorithms. So, there's a lot of technical work here. So, let's get into it. Firstly, a very quick bio. I'm a research partner at Paradigm. Paradigm is a venture capital firm. We focus a lot on investing and researching in all the, let's say, ideas that we create the next. Working with portfolio companies, writing their code, reviewing PRs, auditing, architecture, you name it. And basically, before that, I did the same thing, but with a few companies and I don't know, which others. You can find me in these links, and I'll share them at the end of the presentation. Sorry about that. So, without further ado, what is consensus about? So, consensus in, let's say, decentralized systems is important for it is important for it to maintain, let's say, tolerance to Byzantine faults. Where Byzantine fault, when we say that, we mean that an arbitrary actor suddenly just starts to do crazy things in our network. And we don't want such an actor to be able to interfere, let's say, with consensus, where consensus is when everybody in the network agrees on what the state of the network is. And we have two, let's say, desired properties in consensus algorithms called safety and liveness, where safety says that once something is confirmed, that it is confirmed. So you send your Ethereum transaction, and that Ethereum transaction, let's say, remains part of the chain. And we want liveness, which means that blocks keep arriving. In the sense that the chain doesn't hold, there's no 10 minutes until the next block, and so on.
Georgios, do you mind going closer to your mic because it's not very clear?
Hello.
Yeah, we can hear you.
Okay. So there's a very famous theorem called fault liveness FLP impossibility, which basically says that you cannot have both safety and liveness at the same time in asynchronous networks. Typically, you want to try to have a consensus algorithm that is as asynchronous as possible. But because of FLP impossibility, we need to somehow loosen that in some ways. And we typically do that by adding some extra synchrony requirements in our system, which means that, let's say, we are waiting in Bitcoin, for example, people are waiting for a few minutes until their transactions are confirmed, until they consider them final. It all started with PBFT, which stands for Practical Byzantine Fault Tolerance. This is a very famous paper by Miguel Castro and Barbara Liskov. Barbara Liskov is a Turing Award winner. They're both very popular. You should read this paper, which basically introduced the first kind of practical approach towards getting an algorithm which can get us liveness. So what this means is that if 2/3 of the block producers are honest, we get a block that is not going to, let's say, cancel our transaction later on. And if there's at least 1/3 honest, we can keep getting blocks. And in terms of finality, it is instant, where finality here means that the moment that the block is created, that block is there and it's not going to go away for any, let's say, weird reason. An example of this are the BFT algorithm I said. It's Tendermint, which is used by Cosmos. There's also Hot Stuff, which was developed by Facebook, and there's others as well. But the main, let's say, problem with these algorithms is that the method complexity, which we'll see in a second, it in a sense limits the number of consensus participants that we can have, among other things, which we'll also get into. But basically, right now the biggest production deployment of Tendermint or Byzantine fault tolerance algorithms has been in Cosmos, and we have person, then that person needs to send it to a bunch of other people, and then there needs to be one more round of consent of exchanging of messages and so on. So imagine that we already see a bunch of messages just with 4 or 5 people, and you can very easily imagine how complex this would be if you have hundreds of individuals. So ideally, we should be able to do better, and maybe there is some intuition that maybe if we can loosen this guarantee that they get us, the whole instant finality guarantee, maybe we can get to some better spot. So this was Nakamoto's brilliance, and we can already see from the Bitcoin white paper, which I hope everybody in this group has read, it already says the network itself requires minimal structure. So there's no weird messaging back and forth that needs to be played across all consensus participants. In Bitcoin, we all very well know that there's many block producers, there's many potential block producers, the miners, and they're all hashing at the same time, but they don't need to be connected to each other. So TLDR is a Nakamoto Consensus says that the block producer is voting on which blocks they consider valid, and the chain with the most votes is the one that ends up winning. Obviously, you cannot let anyone to vote for which is the most valid chain, because then anybody would just spam and say, okay, this is the chain, the other thing is the chain, maybe some other thing is the real chain. So Nakamoto said, okay, let's just use proof of work. We will have machines run complex or not so complex computations 24/7, and this will prove that somebody is actually running the thing and they're voting, and their vote actually has some weight behind it. After Nakamoto, there was this guy called Quantum Mechanic on Bitcoin Talk, along with a lot of other people right after him, who said that maybe instead of using proof of work as identity, maybe we could use coins as identity. We won't get into the philosophical arguments on proof of work versus proof of stake and the maybe more practical arguments between the two, but this is just to say that the choice of work or stake is a pure, let's say, Sybil resistance algorithm choice and not the concept. And the whole fork choice rule. And what the fork choice rule is, it really is a function that says, okay, we have many possible chain histories, and we want to collapse the wave function into one canonical chain. And just to maybe visualize this, we can see that here we have a single block, let's say it's a Bitcoin block number 1 with difficulty 100. And for the sake of this example, let's say that, so when I say difficulty, when I said here that the reorgs and the fork choice rule collapses the many possible histories to one canonical chain, Nakamoto Consensus, as defined in Bitcoin, says that whenever a miner mines a block, that block has a certain difficulty. And the canonical chain, the one that our node will follow, is the one that has the heaviest, most total difficulty. So here we see 3 forks. When I say fork, I mean that there is one thing here, there is 1A, 2A, 3B here, and then the third fork is 1, 2B, 3C over here. And if we were to do this from the point of view of an individual node, over the axis of time, I receive block 1, perfect, it has a block difficulty of 100. Then I receive then
Hey, Georgios, would you maybe you can try to hotspot yourself from your mobile? I think the Wi-Fi is cutting in and out, if possible.
yeah, 1 second, sorry.
While Georgios is fixing his connection, I'm sure everyone here who's familiar with the MEB roast knows that we are notorious for researchers dialing in from the beach and various other or the mountains. So please bear with us with this suboptimal audio quality for a real conference, but good enough to get the discussion started as a non-conference. Saria, you will not be disappointed today. I can guarantee you of that, if that's what you enjoy.
Hello, am I back?
Yes, you're back.
I'm so sorry about this. My internet is in garbage right now, and mobile signal is quite bad. Okay, hopefully I'm back. So I'll continue from where I was. So I said that basically we have 3 forks here, each one with various difficulties. And as we progress through time, basically what our node software will do is that first it chooses this thing because this is the first thing that it says. Then after we receive block 3B with a difficulty of 110, it will calculate that the total difficulty is more than what had previously seen. So it will actually switch over to this. And what it will do is that it will discard block 3A because it says, okay, I have another block, it's higher difficulty, I'm gonna pick that because that's. However, block 2B references block 1. So what actually happens is that both the first and the second fork get completely discarded. Our node basically forgets about them and it switches over to this one. And reorgs are a good thing because they allow us to have, let's say, scalable consensus, but they also have some impact to us. And the most obvious thing if you're a software developer is that when you need to do, let's say that you have applied the state 2A, 3A to your blockchain, and then you need to apply the state 3B, you actually need to roll back to 2A and then reapply 3B without having applied 3A. So obviously, this means that your node software will have some memory and disk usage or whatever spikes. There's also some UX degradation because when a chain is getting reorg, you will need to wait more confirmations for a transaction to be confirmed. This is evidently seen by Ethereum Classic on Coinbase, where it used to require, let's say, very few confirmations. But right now it requires on the order of 1 week worth of confirmations, which obviously is not great. And this says a lot about the underlying blockchain stability. And in the DeFi context, because you assumed that 2A had exposed some MEV or whatever, but then block 2A and 3A got reorged, and then you have block 2B. Block 2B will have different, let's say, post-state post-state in the system, which may mean that your arbitrage that you tried submitting here would not succeed if you tried to reapply it on block 2B. So basically, there's a few implications, and maybe there's more. Who knows? And maybe taking it to the very limit, there may be a case where you have many miners trying to mine on top of the same block. This might be because block 1 exposes a lot of MEV, and you want to. I assume that this group is familiar with MEV, so apologies if not, but we don't have enough time to dive into it. So let's say that block 1 exposes a lot of MEV. So some miner will try to claim that MEV. Then maybe another miner, instead of building on top of block 2A, so this could be block 3 or something, they also try to build on top of block 1, and they hash for longer in an attempt to reorg out block 2A. And they want to do that because they want to make money, which is perfectly respectable. And maybe there's a third miner and the fourth miner, and who want to chop to if you haven't an in-depth talk on how this actually works, and all of these are, let's say, excerpts from a blog post that we co-authored a couple of weeks ago. In ETH2, it uses an algorithm called GASPER, which is a combination of Ghost, which is the greedy, heaviest observed subtree algorithm, which is used in Ethereum, and Casper, which was the very popular finality gadget, which was invented for Ethereum. And what Gasper says is that in between, let's say every 6 minutes, there is a block which we call an epoch block, illustrated by this block, big blocks in this picture. And the big epoch blocks, when they are 2 blocks deep, so in this case, this block and this block, they're considered final. What this means is that there can be no reorgs past this block. So once this block is finalized, there can be no reorgs past this block. So once this is finalized, any transactions which happened in between this block and before it can no longer be reorged. However, still has the this block, maybe it gets reorged, maybe not. Whether it gets reorged or not, you will listen to how this can happen in Vitalik's talk. But basically, the takeaway from this is that if you have a transaction that's basically Ethereum 2.0 POS says that past epoch blocks that are finalized, no reorgs can happen, and you still have more or less status quo with blocks that are more recent. So just to give a very quick takeaway, because this was a quite short presentation, in Nakamoto, which is proof of work Ethereum or Bitcoin, there's no finality, no real finality. Reorgs can happen at any point in time. Finality is purely probabilistic. We get, let's say, finality by waiting for 10, 100, 1,000 blocks to be confirmed until we consider our transaction final. Reorgs may be frequent because of network conditions, because of adversarial conditions, because of who knows what. And the fork choice rule, we call it the longest or heaviest chain rule, because we say the one that has the most difficulty. In Tendermint or PBFT, finality comes instantly in the single block as soon as consensus is reached. That big block signals and epoch. And the reorgs are very occasional, and you will see why again later. And the folk choice rule, when we say chain with strongest support, this is maybe a nitpick because you don't exactly have a single person voting for how heavy is a block, like in proof of work, where the miner votes with their work. You have many people voting. Again, you will see that in the presentation by Vitalik towards the end of the conversation, or towards the end of the summit. Yeah, I'm wrapping up here. This is my email. If you have any questions, please email me. If there's any question I can answer now, happy to. Otherwise, we're good. And let me stop sharing. How do I? Okay, I think I stopped sharing. Hello?
Okay, perfect. So I believe we're ready to transition to the next session, unless Tina, you guys do a Q&A.
I think we can do the QA in the side chat if Georgios can stay for a bit. And yes, please go ahead and to give your talk on EVM-based 51% attack and analysis. Looks like we're waiting for Yes to get ready. Sinju, let me know when it's back up. Well, at the same time, Saria, you had a question about Georgios' presentation, about the final takeaway table. So it would be good if Georgios can answer and address these questions in the side chat.